Okay.
So off you go, Enrico.
I will start now. So welcome to this morning session for this second week, if I am not wrong, of the LMS Summer School. So this week, for 5 hours, I will be with you, and I will discuss, as Ian was saying, Monte Carlo simulations of anomalous random walks. And we will go step by step. The main idea is to give you tools to follow and understand a technical paper that was published maybe 2008, which I gave to you in the material of this course. And well, let's see how it goes. So let me start by putting this presentation full screen. Yes. Okay, so now you should be able to see it full screen. And let us start straight away. So today, this morning, we will discuss briefly R, and we will introduce R. Then we will have some introduction also to Monte Carlo simulations in R, and I will propose a couple of exercises at the end of the session. I would need someone taking the time for me this morning, but not maybe this afternoon, because I have forgotten to have a clock or a watch here, but I may also check from the computer later. So for the moment, let us start with the introduction to R. So R is a programming language, is one of those programming languages that have been developed in the last 30, 40 years. And they are programming languages oriented towards scientific computation. And in particular, R has plenty of tools for statisticians and by extension also for probabilists. And they can, of course, also be used by applied scientists if they wish. You might be familiar with other programming languages with a similar philosophy. One of them is very popular nowadays. It is Python. This is used very much in machine learning, and also R is used very much in machine learning. Actually, the two are somehow competing for machine learning, with Python that has been really oriented towards machine learning, whereas R is much more general, if you like. So it has a lot of other features related to statistics, which go well beyond machine learning. But of course, you can use also Python for that. And then there is these two languages, R and Python, are somehow not proprietary. So you can really freely download the compilers or the interpreters and start working with them straight away without paying anything. There is another group of languages that have a similar philosophy, and one of them is MATLAB. This is, on the contrary, something you have to pay for normally. And so the philosophy, the marketing philosophy is different, but the philosophy of the way of working of the language is essentially the same. And here I have put some links to you see, to the information that you can find online on R. Now, let me tell you one thing. Let's say, so for instance, if your university has MATLAB, you would have a lot of help essentially online and immediately available to you while you are programming. And on the contrary, sometimes the documentation of our libraries is not as good. But on the other side, there are plenty of free material online that helps you working with R. So you should not be scared if you are not able to do something straight away with R, but just persevere and you will find a solution to your problem. Not necessarily having to pay for a book. And consider that your libraries may have a lot of books that help you with particular libraries and particular tasks. So what I wanted to go now to show you is the R project page. Working. And after showing this to you, we can go on with the presentation. So apparently, oh, here it is. Very good. Yeah, this is the page of the R project. And you will find a lot of manuals, frequently asked questions, etc., etc. And as I mentioned, you can download it and install into your favorite computer. And if you do not have the possibility of doing that during these 5 hours, I suppose you would like to try a bit something and work with R in spare time, you can still use it online. So if you have a browser, I sent you some links and you are able to use it online, at least for reasonable tasks. Good. Before going on, let me stop sharing the screen for a second and see if there are questions about R. No, I don't see any questions in the chat, no raised hands, etc. So I will go on sharing the screen. And now let us discuss briefly Monte Carlo simulations. I will also give you some hints on why this name Monte Carlo. So what is a Monte Carlo program or a Monte Carlo simulation? It is a simulation or a program that uses pseudo-random number generators for a lot of possible tasks. We will see some very simple examples this morning, but the tasks that are as diverse as computing integrals and simulating random variables distributed according to a prescribed probability distribution. And what is a pseudo-random number generator? This is an algorithm that generates a sequence of numbers with properties that are close, in some sense, to the properties of a sequence of random numbers. So pseudo-random number generators are generating deterministic programs that generate sequences of numbers, and the sequences of numbers have the properties of the sequence of random numbers, approximately, let's say. And normally, all these languages that I was mentioning have embedded with them a uniform pseudo-random number distributor and then generator, generating pseudo-random numbers uniformly distributed in 0, 1. By appropriate transformation methods, I'm not covering all these methods, but I will give you a hint of what you can do. You can generate essentially numbers distributed according to a distribution of your choice. We will see examples with one-dimensional distributions, but there is no limitation. You can also generate multidimensional distributions, etc., etc. And why Monte Carlo? So this is the name of a town in southern France, which is a part of a tiny state, technically independent from France, which is called in French Principauté de Monaco. And this is a place which is very well known for several reasons. One of them is that many rich people from all over the world are citizens of this place because they can in this way pay no taxes or few taxes in their countries of origin. And the second one is that this place is famous for a gambling house, a casino, and it was famous also at the time in the 1940s when these techniques were being developed by people such as John von Neumann and others involved in a nuclear bomb and nuclear reactor program in the United States, leading to the creation of the atomic bomb on one side and of nuclear power stations on the other side. So these guys had to simulate the diffusion of neutrons in a medium. And for this reason, they started introducing Monte Carlo simulations. The method was classified at the time, and it became unclassified only in the 1950s. Actually, in 1953, a group of people published on an application of this method, but not in nuclear physics. That part remained a bit classified, but in condensed matter physics. And I think the authors of this paper include Metropolis and also Teller. So Teller does not, the name of Teller probably is unknown to most of you. Actually, let me try a poll to see how history is changing and how things are going. I will stop sharing the screen again. And how many of you have heard of Edward Teller? I put the name here. We have one raised hand. I can see one. Only two, three. Yeah, okay. 4. Let me wait a second more. I will not ask your average age. It is now 5. Okay, many of you apparently never heard about Edward Teller. So this guy was famous or infamous. He was pushing a lot after the creation of, after the experiments leading to the fission atomic bomb that destroyed Hiroshima and Nagasaki, to create fusion bombs. So it's called the thermonuclear bombs that are realizing nuclear fusion, using fission to create fusion, and which are now available, unfortunately, and are even more destructive. And then he was instrumental for the nuclear, and not only nuclear, but strategic weapon program of the United States up to his death, essentially. So it's very interesting, and it tells us that our priorities have definitely changed, that after the end of the Cold War, in the early 1990s, when you were probably not born yet. So these things faded away, and so now probably only people of your age who are studying contemporary history may have heard about this program and this guy. However, the first paper on Monte Carlo simulations, if I am not completely wrong, is this paper in the Physical Review 1953, and Teller and his probably partner are co-author of the paper. But let me share the screen again. Now let's go back to the presentation. So now you know the origin of because of the use of pseudo-random number generation and the relationship with probability and the relation between probability, the historical relation between probability and gambling. The guys decided to give this name to the technique, Monte Carlo simulations or Monte Carlo programs. And the origin of the method is related to the nuclear weapon program in the United States, at least, let's say. So, not to say that there might be precursors of this methodology, but let's say the method as we know it is coming from that field, let's say, yes. And that field of research. Okay, so next, and R has plenty of tools for Monte Carlo simulations. Indeed, this makes your life much easier than writing everything from scratch. And just to illustrate the technique that we will use later to study diffusion, actually, the kind of problem we are going to address is very similar to the kind of problem that was classified at the time of the beginning of the nuclear weapon program, because we will really start studying diffusion like processes. And the first example that I would like to illustrate with a very simple instance is the numerical estimate of integrals. And the second example is the exponential distribution. So how to start from uniform random numbers in 0, 1 and generate exponentially distributed random numbers. So this is illustrating two possible applications of the method. And let us see first the numerical estimate of integrals. Okay, suppose you want to compute, okay, it's a bit an overkill, but it is a nice example. Suppose you want to compute the integral of a continuous function with support in 0, 1, and you want to compute the integral from 0 to 1 of gx dx. Yes. Now, it is possible to consider this integral here as the expected value of what? Of g of u, where u is a uniform random variable in 0, 1. If you use the expectation theorem, you can see that the expectation of this transformed random variable, g of u, is the integral from -infinity to +infinity of gx fux dx, where fu is the probability density function of the uniform random variable in 0, 1. Remember that this object is essentially the indicator function of the interval 0, 1. So it is 0 everywhere, except in the interval z is equal to 1. So you are just computing by doing this expectation, really the integral from 0 and 1 of g of x dx. And now that you know that, you can use the fact that if you generate n samples, and here there is a mistake, by the way, here and here, sorry for that. If you are generating n samples of u, say u1, un, I will correct this mistake before giving the slides to the organizers, but the mistake is interesting because it will focus us on what we have to do things correctly. So now if we generate n samples of the uniform random variable and n samples that are independent, so this is a sequence of independent and identically distributed realizations of the random variable u, u1 to un, you can approximate the expectation with the mean. And now here you see the mistake, yes? So there should be here g of ui, yeah, the function g of computed in the point ui. And if you are familiar with the strong law of large numbers, indeed, this expectation becomes the limit for n to infinity of 1 over n sum from 1 to n of g of ui. So here there is a g. Let me maybe correct it. So I should be able to comment. Beautiful. And now if I select pencil, I remove this, and then I try to write g of, sorry, I'm using the mouse because I don't have a pen here, g of ui, here it is, and the same here. So this is g of ui. And it is a good time to stop for a that is doing exactly this numerical estimate of the integral. Okay, let me go to R, and let me also open the program generating the integral. And let us first go through this program, which is my first Monte Carlo R program. This is a very simple thing. So, and it is also useful to introduce some of the syntax of R. So you see this first line here is putting a number into the variable n. So this kind of arrow is an assignment. I think you can do it also in the reverse way, but if I am trying to run this line, and then I plot n, I get the value 1,000,000 that I put into n. I could do the same. Let's using equal. So equal and this arrow are similarly. Let's see if this is working. Yeah, you see, you have 3 ways of making assignments into R. Yes. Now you see the difference between this assignment and the equal is the following. So if you have a function with parameters, you will use the equal within the function. You cannot use the assignment within the function. Outside, it is recommended to use the assignment symbol. So this is essentially the less than symbol followed by the hyphen, which creates a small arrow. This symbol here it will give me some error probably, yes. And now, what is the next line here? Here I am creating a million I am creating here, edit copy, a million of uniformly distributed random variables. I am not going to plot all the million of values now, but let me put x from 1 to 10, the first 10 values of x. And you see these are numbers between 0 and 1. And runif is the command that gives you pseudo-random number uniformly in the interval 0, 1. How do you know that? Of course, you need someone who's telling you this. And I can see now 2 questions, so maybe I will stop for a while. But let me just for instance, if you look with a machine, with a tool like Google, or any other search engine, uniform distribution R, you find immediately a help. You see here in the help that the uniform distribution is part of the stats package. The stats package is already embedded into R, so you do not have to explicitly load the stats package, so it's working by default. And then you have different comments here related to uniform distribution that generate the density, the cumulative distribution function, quantiles, and then also the random numbers here. And notice that you can transform the minimum and the maximum to any number you wish to get uniformly distributed random numbers into a different interval from 0, 1. So the default is 0, 1, and n is the number of observation or the sample size. Let me stop sharing, or maybe I can see from here, chat 2. Okay, so there is Jack asking, in this case, we recover the Riemann sum definition. Not really, no. This is just the fact that the integral itself, be it Riemann-Lebesgue or whatever integral is needed, is the expected value of a random variable, and the expected value of the random variable is approximated by the standard mean. So you take the values of the random variable at the samples, you sum them and you divide by n. not muted, but occasionally, if you can hear me now, occasionally my audio disappears for reasons related to the internet connection. So I'm sorry for that, but hopefully this is not hampering too much our discussion. So can you hear me now? If someone tells me or puts something,
Yeah.
very good.
We can hear you now.
Yes, yes, thank you. So I hope this is, I mean, we will have this problem. I know this from my lectures at Sussex and also seminars, etc. But it usually fades away for some seconds and then reappears. And so we don't really recover the Riemann sum definition, but if you like, this expression here is essentially an ergodic theorem, because on this side, you have a time average. You have a sequence of U1, U2, UN, and you can consider the index n as time. And then you compute the function g in U. And then you make your time average. And this one is the so-called ensemble average. So it's the expectation of the random variable, the exact formula for the expectation of the random variable. And this is a corollary, if you like, of the strong law of large numbers, which is the first kind of ergodic theorem you are encountering when you are studying probability theory. Second one, is there any difference between the three methods for assigning variables? I don't understand, Giovanni, this question. Can you please elaborate maybe by taking the microphone and explaining what it is? Please.
I was wondering if there is using the equal sign or the left arrow, the right arrow produces slightly different results, or is there slightly different?
Now I understand your question. Of course, it was clear also there, but I was stuck here in
no worries.
The numerical estimate of integrals. No, yes, no. I don't think there. I don't think there are major differences there. Even if the assignment will not work typically within functions. Yes, so if you have a function, the assignment is not working. You have to use the equal. Okay.
Thank you.
Thank you very much. Good. Okay. Now, this line here is creating a histogram. And also plotting it. You probably can see the histogram on your screen of the random variables. And when I set a flag probability equal to true, this is normalized histogram, which can be directly compared to the density function. Okay, so it is giving us a with probability equal to true. So this is a logical variable, and you have to use this syntax here in order to include it into the function. You have the possibility of having a normalized histogram directly. This is not common in other programming languages. Of course, you can create your own functions very easily, but R has already this embedded in this histogram function. This floor of square root of n is just computing the number of bins in which you put the values into the histogram, and x is the vector computogram. So this is giving us the variable a with a histogram inside. Now, again, you want to know how hist is working. You go online and you have information on the documentation of the hist function. You see that we are using a subset, actually the first 1, 2, and 3, the vector, breaks. Of course, you don't have to write breaks equal, but the position is also important. Of course, if you want to change the position, you have to put these flags here explicitly in your function. Yes. So the histogram function helps you in creating histograms of random variables. And now, by putting the histogram values into a variable, you have different opportunities. For instance, $8 mids is essentially giving you the midpoint of the bin, which you can use to plot things. So this is the plot function, the standard plot function in R. And here what I am saying is I am creating a vector of ones with this command rep. With different settings. So I put the x limit from 0 to 1. The y limit is from 0 to the maximum of x plus 0.3. Then I put a label for the x-axis, a label for the y-axis, and let's see what happens if I plot this. Okay, so the points with their characteristics are plotted here. Now, of course, if you sum the width of the bins multiplied by the height over all the values, you get essentially 1. So you would have points that are above 1 and below 1. But we can compare this fluctuating histogram, which is giving you the estimate of the probability density function with the true probability density function, and this is done with this second command, which superimposes a line plot with ones to your histogram. Now we have a blue line at 1 that I hope you can see. Maybe if I use another color, it is more apparent. Right, for instance. Now you should see a quite thick red line at 1, which represents the theoretical probability density function that you were approximating with your histogram. Now here, of course, if you are increasing the sample size from 1 million to 10 millions, etc., you would get fluctuations that are smaller and smaller. This is also an effect of deviations from the mean, but the mean value of this object here, this fluctuating object here, would be this approximately this theoretical value. So this is always what you are getting with Monte Carlo simulations, an approximation of a probability density function. And now let us move to the integral. Estimate. So this is a trivial code that is computing with Monte Carlo simulations the integral from 0 to 1 of x squared. Let us think a bit what happens for the integral from 0 to 1 of x squared. So it is x to the power of 3 divided by 3 computed between 0 and 1, which gives us 1/3. So this is the famous Archimedes integral. Archimedes got this result first using an analog simulation method by weighting appropriate pieces of metal with the correct shape for this arc of parabola. And then he used the Gaussian method, which is a precursor of analysis, to prove correctly and rigorously that the integral is 1/3. I mean, maybe Archimedes did something slightly different from that, but essentially what I'm telling you is morally correct. Okay? So this is a result that was already known in the 3rd century before the Common Era before. So and of course now we can get this result in one line by computing the integral using our algorithm for integral computation. Now, what happens with Monte Carlo simulations? Well, for instance, I am here generating 10,000 uniform random numbers, and then I am computing the mean of the function, in which in this case is u to the power of 2. So let's try and do this. Again, to find the console, which should be somewhere. Here it is. And what is the value of the integral? So remember that we are expecting 1/3. Okay, we get a reasonable approximation of 1/3. If I am increasing this to 1 million, for instance, or this is even, yeah, 1 million points, I should get a better approximation. You see, this was 0.033468. Now we get 0.33085. If I run the program once more, I get a slightly different value, etc. So this is typical of Monte Carlo simulations, unless you fix the seed of the pseudo-random number generator that you can do in different ways. Every time you are running your Monte Carlo simulation, you will get a slightly different result. And this is very important because this is essentially creating new realizations of your random variables, or of your stochastic processes if you are simulating, as we will do soon, a stochastic process. And the other point to notice here is the approximation. So moving from 10,000 to 1 million, we gained something, but it is not dramatically improved. And the typical error of a Monte Carlo simulation is on the order of 1 over a square root of the sample size. So you have convergence to the correct value, which is quite slow. Yes. So in other words, Monte Carlo simulations are reliable techniques to compute, for instance, integrals, but they may be quite slow in reaching the approximation that you wish. So you might need a lot of computing power, especially, for instance, if you're computing integrals which are multidimensional and quite complicated, as it happens, for instance, in the theoretical particle physics, where people are trying to compute these Feynman integrals in the expansion, in the perturbative expansions of quantum field theories. And they use maybe Monte Carlo methods to approximate these integrals. It takes a lot of ingenuity and a lot of time to get good approximations, and of course, in many instances, maybe even published results might be, well, let's say not wrong, but far from the correct value. Because of these problems related to the approximations of integrals. But I mean, this technique here, as I told you, this is an overkill for such simple integrals, but this technique is essentially what is used professionally by engineers, physicists, and other applied scientists when they need to compute very complicated integrals for their applications. Good. We still have 2 minutes before 50, so let me go back to the presentation and put it full screen. Okay. Let's see if it works. Okay, it does not go full screen, but it will go like that. It's still fine. Just to mention that the next thing that we will see at the beginning of this afternoon will be a simulation of the exponential distribution. So how to move from the uniform distribution to the exponential distribution using a method which is known as inversion method. It's not terribly general because the particular method you will see here is relying on the fact that we can invert the function, which is called cumulative distribution function, but it is general enough, in fact, because numerical inversion is always possible, and there are other techniques, of course, to compute pseudo-random numbers distributed according to a prescribed distribution. But now it is 10 to 11, so it is time for me to stop sharing and see if there are questions or comments related to this first part related to Monte Carlo simulation. So the Monte Carlo simulation is the first ingredient that we will need to understand the technical paper. The other 2 ingredients I am going to present in the next 2 presentations, and one is, of course, the random walk, and the second one is the renewal processes. So by putting all together these 3 ingredients, you should be able to understand what has been done in that particular paper. So the idea is, in other words, to give you all the tools to understand a technical paper that has been published some time ago. But for the moment, I'm stopping here to see if you have questions, comments, etc. So let me start asking you a question. How many of you have already used R? You guys just